day, ladies and gentlemen. We are welcome to our lecture number 9 on Mcen508, that is power electronics and drives. And today we'll start looking at the power electronics concepts for space heating. One thing we need to know or to remember is that around 30% of the electric power used in domestic usage, especially in advanced countries, 30% of it is used for space heating. And we use power electronics concept in order to improve efficiency of that aspect. We use what we call load proportional capacity modulation. That is the technique of power electronics that is used to control the heating system that is used in domestic applications. Before the invention of this load proportional capacity modulation, we have a conventional system which operates the heater, that is the compressor, at constant speeds. Regardless to the temperature of the place, what it does is to maintain constant speed of the compression. And of course, it uses a sensor that will detect when the temperature is at certain maximum, it will switch it off, and when it reaches the lowest minimum, it will switch it on. But nevertheless, whenever it is on, it operates at constant speed. But the load proportional, which is the power electronic version, it is the one that controls the speed of the compressor depending on the temperature sensed in the space being heated. In this load proportional system, the speed of the compressor is adjusted automatically to suit, that is, to be in line with the temperature of the building. So in this case, you can see that we don't switch off the compressor completely. What it does is that it sometimes increases the speed whenever the temperature goes below certain threshold, and it reduces the speed when the temperature goes beyond certain threshold. So in this way, we minimize power losses which is incurred in the conventional on and off switching system. And this is the block diagram of our proportional system. We supply our power from the mains 60 Hz, but in Nigeria, you know, our frequency is 50 Hz. So that power supplied is delivered to our speed controller. That is the drive that controls the speed of the compressor so that it will suit the temperature of the place. And it is this converter or drive converter that operates the motor that drives our compressor that distributes the heat throughout the building. And this is my heat pump. That's the compressor, which is being driven by the motor. The motor can be 3-phase if it is for large application, and of course it can be single-phase if it is for smaller applications. And the types of motor that are used is either induction motor or synchronous drive. Synchronous motor. So there are drives which we discussed in our lecture number 8 are used for adjusting the speed of the heat pump, that's the compressor. And from this diagram, you can see that we have a free space here, which means the system is off, and we have this waveform, which means the system is on. So you can see that even where the system is on is divided into two. We have a shaded area, and this shaded area stands for the amount of heat that is lost during that switching on and off operation, and while the white area stands for the actual heat that is, the energy that is used for operating the system to distribute the heat in the system. So if we take the average, you can have as high as this level to serve as our loss. The loss that is incurred, just as I discussed now, in our conventional on and off system is eliminated if we use the proportional capacity modulated heat pump. And of course, there is still some losses that is incurred even in this proportional capacity modulated heat pump, but the total heat loss is reduced by around 30% if we replace the conventional with the proportional capacity version. This is one advantage. It reduces the wastage of energy, and of course it makes the building very comfortable because it senses the temperature and control the speed of the compressor so that the temperature can be somehow maintained within a very narrow band, that is within a suitable limit. That is the application of power electronics in heat control or heating control in domestic applications. And of course, similar system is used in industrial applications. So we now look at another application of power electronics for operating fluorescent lighting. We know the lights basically is of two types, though now we have some additional ones, LEDs and what have you, but the conventional ones are either fluorescent or incandescent lighting. This lighting also, it consumes around 15% in residential electricity energy requirements, and it consumes around 30% in commercial buildings. And the fluorescent lights, as compared to the incandescents, they have higher efficiency of 3 times or even 4 times compared to the incandescent lamp. So that is why they are used mostly, especially in industrial applications. The efficiency of these fluorescent lamps can be increased by around 20 to 30% if we operate it at a very high frequency, because we know the fluorescent light is connected directly to our AC, which is at a frequency of around 60 Hertz in other countries. In Nigeria is 50 Hertz. But if we increase the frequency, that is where the application of power electronics comes in. If we increase the frequency to a high value, the efficiency can be increased by 20 to 30%. But we need to also know that the fluorescent lamp, they have a characteristic of having a negative resistance, and I have already explained negative resistance in one of my lectures. It's a situation where you find that the current is increasing, the voltage is decreasing, and vice versa. Now, for this reason, always there is what we call a choke, inductive ballast or choke, that is inserted into the fluorescent lamps for it to be controlled so that this negative resistance can be eliminated for it to operate normally. And for us to see that, this is the typical circuit diagram. This is my fluorescent lamp, and I connect my ballast, that is the choke, in series with the lamp in order to address the problem of that negative resistance. And as you can see from this cup, this is the cup representing my lamp. As you can see, when the current is increasing, the voltage is coming down, and that is what we mean by negative resistance characteristic. So we now insert our ballast, which has a characteristic of like this, and at the intersection, that is where the operating point is reached, and the fluorescent lamp will now be operating just like any other lamp with positive resistance, not negative. And the impedance of this system is generally resistive, and for this, the equation relating the voltages, that's the voltage of the ballast, that's the choke, and that of the lamp itself, and the supply voltage is given by this. That is the square of the ballast voltage plus the square of the lamp voltage is equal to the square of the supply voltage. And as I've already mentioned, these two curves, the curve of the ballast and the curve of the lamp, they intersect at a point, and that is where my operating point is reached. And as I have mentioned, we use the fluorescent lamp because it has higher efficiency compared to the incandescent. But we said if we want to increase the efficiency by 20 to 30%, we should change the normal conventional frequency of 60 or 50 Hertz into a higher frequency, and that is where the application of power electronics comes into play. And look at my circuit. this is my utility input, that is from the main supply. I will now connect it to my power electronic circuit that will change the normal frequency, the 50 or 60, into a very high frequency, and that high frequency source will now replace the choke we have used. And how do we generate this high frequency? Simply by this simple block or circuit diagram. What we do is we take our input from the utility, which is at 50 or 60 Hz. We use a rectifier diode to change it into DC. We use a capacitor in order to filter the ripples, while the DC now is delivered to an inverter, a high frequency DC to AC inverter to a very high frequency, and it is this high frequency that will now be connected to these lamps, so that the high frequency supply will increase the efficiency by 20 to 30%. And normally we set the conventional frequency from the mains is 60, but in Nigeria is 50. But when we use this high frequency circuit for conversion, we get around 25 kilohertz to 40 kilohertz. And of course, before we even rectify it using this diode, we use what we call electromagnetic induction filter, and its function is to suppress any electromagnetic induction interference at the input, so that we can have a clear and stable output. That is the application of power electronics in operating fluorescent lights. And we now look at another application of power electronics for induction cooking. In normal electric cooking, there is a very large amount of heat that is lost to the space, to the surrounding, because the heating element, when it releases the heat, it will go through the space before it reaches maybe the pot or anything we are using for cooking. So induction cooking is used in order to save that amount of energy that is being radiated to the space. And this is the circuit diagram. My AC supply from the 60 Hz or 50 is now delivered to a rectifier and high frequency inverter, just like the previous one I have just said. This high frequency, it has ability of generating very large amount of heat because of this high frequency. And when this supply is connected to the induction coil, it will now be generating large amount of heat. And this coil will now be in contact directly with the metal pan, so that the heat generated by the induction coil will be absorbed directly by the metal pan. Therefore, the loss to the space is drastically reduced. And just like in the previous case, the frequency is changed from 60 or 50 in Nigeria to 25 to 40 kilohertz, and it supplies the circulating current in the induction coil, as I said, as very high frequency, and that high frequency will now be the source of our heat that will be hitting the metal fan directly. Then we look at the application of our electronics for inverter welding machine. The welding machine are typically the arc welding machine. It uses a very low voltage at the output, around 50 volts. That is, we take around 240 from the mains and step it down to around 50 Hz, but the current is raised, sometimes up to 500 amperes, because the higher the current, the higher the heat generated, and it will have that melting capacity for the arc welding to work suitably. The AC input voltage is first step down, that is from that 240 to 50 Hz, or any suitable voltage, because this 50 is just a reference, and it is then converted into DC using what we call a controlled DC circuit. And then we use a very large inductor in order to filter out all the ripples in the DC generated, and this DC is finally converted to a very high frequency using inverter, just like the one we have seen before. We rectify it, we filter it, and then we use DC to high frequency inverter to generate very high frequency, and that high frequency will give us a very large amount of current, which will consequently give the amount of current required for the heating, for melting the welding electrode. So thank you very much, ladies and gentlemen. This is the end of this lecture. Till we meet in our lecture number 10. Thank you.